And this again is one of those things where, first of all, I don't feel that I'm really qualified to tell you lots and lots of information about NumPy and SciPy. I've been using them for a while, and I still feel like I've just scratched the surface. So I'm going to give you an overview of these things, and even if I wanted to, it would probably take me a couple hours to tell you what I've come across in NumPy and SciPy. Okay, so we'll start with where to get information about them. I'll talk about how you can use them. I'll talk about how you do linear algebra in NumPy. It's really good at that, really, really fast. And then I'll talk a little bit about SciPy. Okay, so NumPy is I think about a second or third generation math package for Python. The first couple ones had limitations, so people kept going back and redoing it until they got it right. And they've learned an awful lot, and they've built an awful lot into NumPy. SciPy is a package that's built on top of NumPy, and NumPy is actually now part of the SciPy or toolkit, and does all sorts of stuff you might want to do scientific calculations. As I've come to a couple times when I've been talking, Python is not the speediest of computer languages. It can be, if you want to do something which involves looping over a bunch of times, loops run relatively slow. However, the neat thing about NumPy and SciPy is that it does an awful lot of stuff potentially with one call. Well, because Python's not looping, it's going off and calling some built-in routine. That built-in routine can run really fast. As a matter of fact, that built-in routine will probably run faster than if you had tried to do the same thing in C or Fortran yourself. Why? Because it's been optimized by people who are really, really good at writing numerical algorithms, and they may have written it specifically to run on the computer that you're running on, and they'll do it a different way on a different processor. So if you can do something in NumPy or SciPy, the odds are you're going to be able to do it very fast. Yes, Jeremy. Absolutely. Absolutely. Well, that's true of all of Python. When we call a command in Python, it could be using other Python statements to do that for us if we call a package. But it could also be done in C code or Fortran code. And in the case of NumPy and SciPy, it will be calling both C and Fortran to do some of the things we call it. Now, I'll give you an example of, I think a little bit later, where I'll use interpolation in NumPy, and it's pretty fast, but it's not as fast as I think it ought to be, and I'm not sure about that, why that's the case. And that may be because it's doing lots of checking that it doesn't need to do for me, but it might need to do for other people. But so it's possible that in that particular case, I might be able to do better by writing my own C or Fortran code for that particular task. But in general, if you're using NumPy and SciPy, it's amazing how fast it will be. And just as an example, I was talking earlier today with Bob Von Driel, and he was comparing some code where he was running some things that he was doing in Fortran versus doing the same calculation but having NumPy and SciPy do convolutions with Fourier transforms, and he found that going from his Fortran code to doing it in NumPy went from 45 seconds down to about 3 seconds. And Bob is not a slouch when it comes to Fortran programming. Okay, so there's lots of stuff out there. There's a free book by Travis Oliphant. It's a little old, but probably still pretty good. There is an incomplete Python tutorial. There's a SciPy tutorial, which is still growing. There's an incomplete user's guide. There's lots more stuff out there, including a nice document called NumPy for MATLAB users, which is even useful if you don't know MATLAB, because it's got all sorts of stuff that you might want to see. And then there's the documentation, and this stuff is really good. So these are the reference guides, which have everything. How do you access NumPy or SciPy? You just do an import. So import NumPy, or better yet, since typing NumPy all the time gets tiring, you might want to do an import NumPy as NP. You'll see in some examples people doing imports of specific routines, or even worse, importing everything. Really not a good idea, particularly not when you're writing scripts, because then you can have this namespace collision problem. And furthermore, when you're looking at your code, when you see np.array or numpy.array, it's bringing forth, it's reminding you that's part of NumPy. Okay. Having said that, there is a nice shell that comes with nthought Python. It's not available for the APS share Python, called IPython. And if you say ipython.-pylab when you call it, or on Windows, I think you just get a pylab icon, and you'll see this extra little message here. Welcome to pylab, which gives you matplotlib and NumPy as well. Excuse me. So, and you can find out more information by typing help pylab, just as it goes there. So, if you want to, you can just start by going ahead, and you can access from this the routines without the NumPy array, but it defines for you the NumPy prefix or the NP prefix. So in this case, I'm calling array 3 different ways. I'll tell you what it means in a moment. If you get really comfortable, you may want to be able to start doing things where you just type array, but in the beginning, and sorry that I keep emphasizing this, use NP or NumPy until you're really used to this stuff. Okay, so let's talk about the most important part of NumPy, which is arrays. Okay, if I pass it a list or a tuple of values, it makes an array for me. And this is an array, which I can find out its shape, has got 1 dimension and its length 4. Okay, I can create a 2-dimensional array by nesting lists or tuples inside my list or tuple. Okay, so here is a 2-dimensional array. And if I look at the dimensions of this, I see it's 2 by 2. Yeah.
Is that first line in your second example on this type?
Yes. Yes. Let's see. No, I don't think so. I have a tuple and I have a list inside a list. Is that what you're asking? Yeah. No, that is not a. I intentionally did that, really, to show you that it doesn't care whether they're tuples or lists. But you'll notice that, and here I did it with two lists inside a list. And either way, I get exactly the same thing. You can, yeah. I'm not. Let's see. I don't think you can put an object inside an array, but I might be wrong on that. At least I certainly haven't done that. It's not. It actually is going to, when it creates the array, it's going to allocate memory. It's going to do a copy. It's not. These things are not linked. If that's what you're saying. Yeah. These are the array is not the array. At least under normal circumstances, is a new object. Okay. You can also change the dimensionality of something. So here I have made an array with 8 values in it, 0 to 7, and then I've said I want to make this a 2 by 4 array or a 4 by 2 array by reshaping it. Okay, that's often common. I can also reshape it to be a 2 by 2 by 2 array. I'm not limited to just 2 dimensions. I don't know if there's any limit at all to how many dimensions you can have in an array. Now here's where things get a little bit tricky. I can ask for element 1 of my array. Okay, element 1, of course, is the second element. If I reshape it, I need to be a 2 by 4. I need to use 2 indices to address it. So here, element 1 comma 2 brings me to this one right there. And if I do 2 comma 1 on the 4 by 2, I'm addressing that one there. And then finally, if I reshape it as a 2 by 2 by 2, I need 3 indices to address an individual element. Yeah. What order? You know what I do? I have to sit down and figure it out each time I do it. Let's see. So you can see that the 1 is taking us to the second level here. So that's got to be. So it's got to be going 1, and then the second level is going to be. Well, it's not obvious from this example, but you can work backwards. Okay. So so that's the way that it works. But and honestly, I have to check each time, and I have to convince myself. Although for a lot of the things I'm doing, it doesn't matter, because all I have to do is to make sure that it doesn't really matter which plane I'm working on, because I'm just got to get the right section, and I can test it by doing some test calculation and seeing, yeah, that indexing gave me the part of the array that I wanted. And particularly that's true when we start getting to slicing. Do you remember slicing from when we worked with lists? Well, we can slice arrays too. So here, for the first element, I use a colon. The second element, I use 1. So it gives me this list here, where it gives me every possible value for the first index and just 1 for the second index. Okay, I can say partial lists. I can say starting with the third element and 1, that gives me these 2 elements. I can use a tuple or a list as well. So here I'm specifying the first and third. That circle should be around these 2 circles should have been moved down, so they cover the 3 and the 7, because that's what I get there. So I messed that one up there. And we can assign to those elements as well. So here, this code has pulled out the 3 and the 5, and if I assign those to be a list of values or a tuple of values, I've changed this one to be -1 and this one to be -2. Or I can use a single value, in which case it gets broadcast, so my -1 ends up in every element. Okay? But that's not all. We can do operations on arrays as well, and it's really, really fast because it's all done in C. So here, just to give you a more complicated array, I've taken the numbers 1 to 2. I've multiplied them by 5. When I multiply a list by 5, I get the list 5 times. Okay? And then I've reshaped it into a 3 by 5 array, so 0, 1, 2, 0, 1, 2, 0, 1, and so on. And that's my array. So I can do various things with them. If I say A plus 4, it adds 4 to every element. Great. If I say A times A, it multiplies my arrays by itself, element by element. If I ask, is the array equal to 0? Well, it gives me back a new array, which has true where this is true, and false where that statement is false. All these things are being done in one line of Python, and they're being done really, really fast. So let's see, actually, what did I do here? And here I do a test. Is A equal to A times itself? Okay. Well, that's going to be true for 0, and it's going to be true for 1, but it's not going to be true for 2. So you can use this in an expression. Yeah.
I noticed that the last one, it tells you what type it is, if it's a Boolean.
Right.
Can you print that out by putting a position into the array? Or
No, you'd get that by type. Okay. You'd call type on it. Okay. So let's see. Yeah, sorry. Oops. Excuse me for a second. I have a meeting with Lynn coming up in 15 minutes. Yes. Here, in all these cases, I've not, here, in none of these cases have I changed A. I have not changed A. I have defined a new object, which is going to go away very shortly, because I've never said something equals these values. So here I've defined a new array, which is A plus 4. And if I had said A equals A plus 4, my new array would have been that. And here, but none of these cases, and this is where I got myself a little bit confused when I looked at this. Here I've done A times A, and then I'm just testing to see if it's equal to A. But at first I looked at that and said, wait a minute, why do I have an equal sign there? Okay. And again, I probably shouldn't keep emphasizing this. Python, it can be slow, but this stuff will run as fast as you could do it in any other language. There is no loss of speed in doing any of this kind of stuff because you're using Python. Okay, now this is a logical array. Okay, it's got a value for every element in our array. We could use that as a way to index our array as well. So starting again with our same array, if this isn't a very useful thing, but if I say A equals 0, then I've created a logical array that's true for every element that's 0, and then I've indexed by it, and I get an array back which contains all the 0 values from my array. Concept's useful. In practice, this statement is one you'll never use because all I've gotten back is the values that I already knew. I might want to know how many are there, so asking for the length of that might be useful. But this in itself isn't. This is useful. This gives me a copy of A. So now I have two different matrices, two different arrays, and I can manipulate them independently. This is something that I might use. Take all the values where B equals 0 and change them to 3. So now I've taken this array here, I've made a copy of it, and I put a 3 every place where I had a 0. And notice that because I made a copy of B, my array A hasn't changed. But if I just simply said B equals A, then A and B would point to the same thing, and then I would have had would have changed. It would be the same. They both would be the same. Yes, question.
So you said that you haven't tried arrays with objects, so you can't create an array of arrays?
You know, let's play with that later. I don't offhand. I think that I don't. My feeling is that all objects in an array have to be the same type.
Okay, so if you created an array of arrays, you could do it?
Boy, I just don't know. I just don't know. As I told you, there's lots in NumPy I haven't done. I've never used an array for anything other than numbers. Now you can use it for floats, you can use it for ints, you can use it for complex numbers. Strings, yes, you can put strings in. That's definitely true. What else? I'm not sure.
Because I was thinking like having an array of numbers and then having an array which tells you if those numbers are equal to something or something like that. So you have a boolean associated with a number, and then have that in the array so you can call those both.
You could, but I don't see why you'd want that inside your array. And you might have run into trouble because now you've got things of different types. I don't think you can do that. But you can certainly create a higher level object that contains your objects. Okay, so let's talk briefly about linear algebra. Lots of linear algebra can be done. You can call np.zeros to create an empty zero matrix filled with zeros. np.ones will give you a matrix where every element is 1. More useful than either of those is to create an identity matrix where the diagonal values are 1. If you want to do, you're probably not going to want to do too much element by element multiplication. You're probably going to want to do dot products, inner products, cross products, those sorts of things, and they're all defined. Okay, you want an inverse, you just ask for the inverse of the matrix. How big? Really big. If you want to get a range of values over some, with a range of values of floats, you don't necessarily want to get them with integral values, 1, 2, 3. Linspace will give you a range of floats over some range. You can also do the same thing with logarithmic space. It's got, you can also have, it's not really linear algebra, but you have fast Fourier transforms available for you as well. And there's a nice example list, if you go through this, showing you how each of these calculations works. Okay. One thing that's different from what you've seen so far is that NumPy does not throw exceptions when you do things like divide by 0. Why? Well, because when you have a large array, you want to do what you asked it to do, and if there happens to be one out of bound value, you want to get the rest of the values anyway. So what happens if you divide by 0? Well, here I've taken this array, and if I divide 10 by that array, you see I get 10 for the 1, but I get I and F for infinity as values for where I've divided by 0. If I divide by minus 10, I get negative infinity. So I divide negative 10 by it. And if I try to take the square root here where I've got this square root of this array where I've subtracted 1, square root of 0 is fine, but the square root of minus 1 is NaN, which stands for not a number. Okay? No exceptions, no problems. But if I want to test for these things, I can do NP is nan or is infinity. And that will come back with a test that tells me true or false on which elements are either not a number or infinite. So I could, for example, do a index where I change all these not a numbers to be 0 by saying index my array by array dot is not a number. And that'll give me back a logical array. Okay. What about when I want to do something different depending on whether the value is, let's say, positive or negative? Okay. So I want to use this calculation method for except where b is 0. For the 0 values, I want to use what's in here. Okay? Well, you can't do that conditional processing fast the way you would want to, where you loop over things, look at an element, and decide what to do. What you do instead is you evaluate either one, and then you use this where statement to collate. So what this statement will do is it will give me the value of A where B is 0, but it'll give me the value of B where B is not 0. And this is, again, really, really fast. Okay? Most of the time, when people call this in practice, they put some expressions in here. So here's an example. I want S minus D where D is positive, but I want S plus D where D is negative. By the way, I could have done that much more simply by just simply saying S minus absolute value of D. But I don't know which one's faster, by the way, but they're probably comparable in speed. So this is a typical case where I've written a test and I've written two expressions, and it looks like it's going to take either one of those expressions, depends on what's here. But if you think about it, you realize it has to evaluate all this stuff before it calls where. Okay? And it is possible to nest one where inside another. Not sure that's the clearest code to read, but it's possible. Yeah? So is it fast? Well, it depends on how long it's going to take to evaluate your expressions. But in almost all cases that I can think of, unless you're doing something really, really that takes tremendous amount of processing to calculate both branches. It's going to be faster to calculate both branches and then just take the one you want using the where statement. But that, I mean, if that's not true, then Python is probably not the right language to be doing it in. Either that or you really need to think about writing that code externally. Okay, so let's go on to talk a little bit about SciPy. I don't have much time left, but I don't need it because I'm not going to talk a lot about SciPy. SciPy has lots of stuff in there. Okay, these are the submodules within SciPy. I'll give you a very short example. Okay, and it's related to what I was talking about with Bob. The goal I had when I was doing some work with him originally was to evaluate a peak shape function by computing the peak shape functions, taking the Fourier transform of the peak shape functions, multiplying the Fourier transforms, and then transforming them back. That's known as convolving. Okay, and then I normalize that convolved function to make the peak, the top of the peak 1, and then I interpolate them onto a grid. And what the interpolation does is it gives me a function that I can call anywhere I want to, and it gives me the value of that peak shape function on any arbitrary point. So actually what's interesting is that this approach we dropped, we're now back to using it again for other reasons, even though it wasn't quite the fastest way to go. So let's take a quick look at how I do that. So I define a function. I use linspace to give me a grid of linear points, where points is the number of points, from minus the width to the plus width. Okay, so I get n points over that. I create an empty array. This is just tells me how many points I want and sets them all to be 0. I create a figure. And then this code is a little bit tricky, but I'm going to take some things that I've passed in, some scale values and some distributions. This turns out to be just some values, and this turns out to be a pointer to a function. And I zip them together. That makes pairs of them. Enumerate sticks a number on the front of each one, so then I can just count them. So this gives me, the first time through, I is going to be 0. Scale is going to be whatever the value in scales, first value in scale was, and dists will be a pointer to whatever the first value in dists. And then I call that. So here I call dist, which I've pulled out of the list. I've passed it a value for an array of x values. And one of the arguments is the scale, which I've pulled out of scales. And it gives me back a list of z values. Okay, and then I plot them. Okay, so then I call Fourier transform on these z values, and it's going to stick that into the, actually at this point it's calculated all of my curves, and it's put them into into this z array, and then I calculate Fourier transform of that. Then I do a bunch of stuff in a very complicated call. I take the product row by row of my z array. Then I take the inverse Fourier transform of that. Then I shift it and take the real component of my Fourier transform. So that's my convolution. And then I shift it by half a point because I'm doing a discrete Fourier transform. And then finally, I call an interpolation function on these values. And here you'll see I've got p as my product. I just divide p by the maximum value in p. That normalizes it. So now I've got everything scaled so the maximum value is 1. This calls my interpolator. So that defines my routine. It does in very small number of steps. It's done a bunch of, it's done my convolution, and it's done it in a symbolic way. So then I can run this, again with a very small amount of code. So I give it 2 distribution functions, the normal distribution function and the Cauchy or Lorentzian. I give them widths. So those are the 2 things I'm going to pass in. and I'm going to say that my width that I'm going to do the calculation over is 10 times the width of the largest here. So then I call my peak shape function. That returns a new function back for me, and I calculate a new spacing, and I calculate now many more points than I used before. And so I plot the convolution here, and that's what I get. So this is in this code, from this part here, I get this graph, and I can see the two functions that I put into my convolution, and here I can see the output of the convolution. So I'm running through this fast. I apologize for that. I'm not so much trying to show you exactly how it works. You can go figure that out line by line, looking at what it's doing. But to give you an idea of how you can do a pretty sophisticated thing in NumPy and SciPy. And as I mentioned, I found out this morning that Bob took somewhat similar code to this, benchmarked it against his old Fortran code, and found out that this is much faster. Factor of 5, or maybe no more than 10, I think. Okay, so that's it. To give you a feeling for what NumPy and SciPy do, if you're going to work with it, you're going to need to spend time learning it. Maybe at some point, somebody, maybe me, maybe somebody else will spend more time talking about NumPy and SciPy, because there's a lot there. Maybe we'll get somebody out from NThought someday. That would be nice. Okay, questions? Anybody still awake? Okay. All right. Thanks very much, and hope this was helpful.